I'm sorry if I cough through this, but I thought a few of you might want a summary of what we talked about today regarding the elevator lab at the beginning of class. So the first thing that we did was we talked about how on the first page of the handout, there are really only 3 possible diagrams. One where I have equal forces, one where the upward force is bigger, and then one where the upward force is shorter. Okay. Now, the reason why I am talking about the upward force being shorter or longer is because the downward force traditionally represents weight, or the force due to gravity, and that is a function of your mass, and your mass is not changing. Your mass does not change as a function of your motion, or it's not related to your motion. So the motion description for the one on the left was either at rest or constant velocity. In the middle, we were moving up and speeding up, or moving down and slowing down. And then the next one was, I'm just going to move it over. And many of you will probably want me to redraw this so it's not quite so ugly. All right, that's a little bit better. So for this one, we have moving down and speeding up, or moving up and slowing down. So each one of those will be used to describe what's happening in the elevator. So the thing that's important to realize is that your weight never changes. And so what that means is that the scale does not read your weight, because the scale reading does change. So the scale reading changes. So it cannot measure weight because your weight does not change. Hopefully you know that. So what does the scale measure? Well, I've got 2 forces that are going up. If I were just to do a free body diagram, I know that the upward force is the normal force. If weight is the downward force, that means the upward force is the normal force. And so the upward force is Fn, or the scale reading. So when you are doing your scenarios and you draw a free body diagram, so suppose I'm going to do, this is one of the boxes. I don't remember which one it was, but we're going to say at the bottom, moving up. You must put in a free body diagram. And we know that this one is equal to the force due to gravity. And this one is going to be the scale reading. And you will actually put in those values. On the board, I wrote that the force due to gravity is equal to, I might not have written this part, but it is equal to your scale reading at rest. Why am I making that claim? Because at rest, I know that the force of gravity is down. I've got the upward force is the normal force, which is, this is the force of the scale. These are equal to each other. So force due to gravity is the scale reading at rest. I know that the force due to gravity is also equal to your mass times the gravitational constant. I talked about this on the day we said everything you want to know about forces. And for Earth, G is equal to 9.81 newtons per kilogram. So suppose my scale reading, so let's do an example. It's in pink. The scale read 520 newtons. Okay. That means that my force due to gravity is 520 newtons. That's equal to my mass times 9.81 newtons per kilogram. Divide both sides by 9.81. So I'm going to have 520 newtons divided by 9.81 newtons per kilogram. And that is going to be my answer in kilograms. I'm going to do that real quick. If you just use 9.8, that's fine. And so this gives me 53 kilograms. And this is equal to my mass, not force. So in order to find my net force, I know that F net is going to be force of the scale reading plus my force due to gravity, and this is going to be my MA. This is up, this is down. So when I put in values, let's just suppose for the sake of argument my scale reading going up was 600 newtons. Down, I'm going to have to subtract 520 newtons. So that gives me 80 newtons. That is equal to MA. I just calculated my mass, and so I use that to find my acceleration. Okay? And this right here, that is the calculation of my net force.